To discover the things we discover, we don't actually send any packets on the network. To collect the data and aggregate it in one place, we do use the network, but that's our application talking to our application. So the discovery is continuous and extensible. So when things change, they change pretty. When things change, you notice, and the database gets updated very quickly. That might be seconds, it might be hours, depending on how you have it set. But compared to the scale at which people operate, that's quite fast. So it also does extensible exception monitoring. Notice I didn't say statistical monitoring. That's an interesting and important thing to do, but we don't do that. And when I say by exceptionally scalable, I mean more than 100,000 systems should not be a problem. And you'll see why that is. And that's the part that usually people gag on. So, and everything we put in is in a graph database, central graph database. Oh, there we go. Unfortunately, Impress Remote has stopped. It did that the other day. So we'll forego that. And oh, apparently it's hung this too. This is wonderful, isn't it? Okay. Oh, that let go of it, so back up. So how many people in the room here have some kind of monitoring system? How many of you have some kind of discovery system that creates a CMDB that's automatically updated? Very small percentage of people by comparison. And most of these are probably, in this crowd, mostly open source. Is that correct, including for the discovery or not? Closed on the discovery? Yeah, that's kind of what I suspected. So how many people here are happy what you have with monitoring? Discovery? Yeah, okay. This is my market research, guys. So thank you for your assistance. So I started looking at this project when I was working on a computer that had 2.25 million cores, which is a pretty good sized computer, and it was for, well, that three-letter agency that's been in the news a lot. And because of this, we had concerns for extreme scale, and I can actually mention that because there are actually, if you go look up PsyCop64, you can find out about it. And it had a cube topology, so you had to be topology aware, and I started thinking about this, and I realized that I had some ideas that were interesting. And so I started out this project as really about monitoring. But as I went on, I've added this discovery and realized that for most people, discovery is the piece that they don't have. It's the, as you can see by their hands raised in the audience, the piece that people are sort of missing out on. And we sort of went to added topology discovery. Now we kind of discover whatever you want. So as I give this talk, I give it what I call it in 8 dimensions. And so someone here in the audience probably knows what this is. This is an 8-dimensional hypercube compressed into 2 dimensions. So I'll use this to remind myself that I'm changing gears and changing dimensions in the discussion. So the 8 dimensions we'll cover are the problems we address, the capabilities that the system has, how we distribute the work, which is some philosophical kinds of things, the components, the architecture that supports this, the components that go to it, a little about the discovery graph schema, the API for discovering, which is this extensible API. People already know how to write APIs for monitoring, so I won't talk about that. And the status of the project and the project's needs. My purpose for coming here is community building. Although I mentioned marketing, really it's community building. I'm looking for people to come alongside and say, oh, this is exciting, I want to help. This is what open source is about. So the first dimension of is the problems we're addressing. One way of looking at system management, most of what people do for systems management is about risk management. You know, you get stuff up, and that sort of takes a little bit of time, and all the rest of your life after that is spent about risk management. One way or another, risk management. Whether it's, you know, fixing problems, avoiding problems, keeping things up, all those issues you do have to do with risk management. So what the things we do to help that are we maintain a detailed discovery database. You could call it a CMDB if you like. For those of you who like ITIL or whose managers like ITIL, a CMDB, Configuration Management Database. We discover systems that you've forgotten about, which is an interesting thing because about 30% of all break-ins that come in from the outside come through machines people have lost track of. It's really good to have tools like Puppet or Chef, but they only manage the systems they know about. If you think it's been retired or you haven't yet put it under Puppet or Chef because it's an experiment of some kind, then it doesn't know about it. So this is the truth. When you look at the data, about 30% of the break-ins come through systems that are no longer being maintained because people forgot about them. We also discover what licensed software that you have. Now, there are two kinds of risks with that. One is the risk you're paying too much money, since Oracle, for example, is very, very proud of their software. And it'd be happy to charge you quite a bit of money for extra copies that you don't actually need. And in the US, at least, the risk of having too few licenses cost you about $500,000 to start. That's for anything. So there are significant financial risks associated with that. We also monitor servers, systems, and switches. And when you monitor those services, that's about risk mitigation as well, trying to make sure that you have the opportunity to fix it sooner rather than later, so that you know before your customer calls you that you have a problem. You can say, yeah, our guy's already on it, even to the first customer. And of course, one of the other risks is if I have a service that I'm providing and I'm not monitoring it because I've made an error, or something is slipped between the cracks, then how many people here have things slip between the cracks in their administration? Yeah, okay. Gosh, I've never seen that myself, except on the systems that I've managed, right? So one of the things that can happen is you could be offering a service and not monitoring it. But because we discover all the services that you're offering, we can tell you through a graph query, you can ask the question, tell me what services I'm offering but not monitoring. So as I said, to summarize, we're doing intrusions, licensed software, audit risk. Audits are a piece of this as well. A lot of public companies have very formal public audit kind of procedures. And this data, having it there all the time, means you're ready on any given day for an audit. So from a DevOps perspective, why do you want discovery? Documentation. Anybody here think their documentation is complete? Correct? Yeah, okay, that's the usual answer. Sometimes one or two people raise their hands. But the point is that means there's an opportunity here to fix a problem that people have. How many people think they know all their dependencies? Excellent. One person. That's sort of normal too. But so if you want to do planning, let's say you have a process that you want to say, we're managing all this stuff in this fashion, and we want to transform into managing it this way. In the process of transforming the two, you want to know exactly how it really is, what state you're at the moment, and whether you've actually achieved what you intended to at the end. And if you have a complete and up-to-date model of what you have, well, then you can see that a lot more readily than if you don't have such a model. And as I mentioned, ITIL CMDB is kind of a buzzword thing that a lot of people have to have for compliance reasons or internal politics or other reasons. And that's what this really is. And our property of our discovery is that it runs continuously, yet it's low profile. So then switching to the second dimension, right? The second dimension is to talk about the features we have to support this. And I recall there's about 11 on this list. The discovery is continuous. The footprint for discovering this data, we discover it by listening. Most of it by listening. As my mama used to say, it's amazing what you can learn just by listening. So we listen. And a lot of this stuff is already discovered by the operating system and listening, or we ask it. And the rest, we listen to the network, but only to things we're allowed to listen to. You don't require network privileges of any kind. We notice everything that changes. Oops, I didn't quite finish that. And we discover dependency information, although that's not as reliable as we would like it to be. Some is better than none. One of the things that's interesting about discovery and monitoring is that they're tightly integrated. So our discovery drives our monitoring. In fact, that's a relatively recent piece of code that's stuck in there to make it do that. And they're both easily extensible, scalable to a large number of systems. The exact number is not clear, but 100,000 is clearly in range. Server failures are distinguishable from switch failures, interestingly enough. And so you don't, for example, get a switch goes down and I get 48 sudden reports of failure, in fact, when you've only had one switch fail. And we're in the process of re-architecting to add multi-tenant support. So this is the part that sounds maybe a little unreasonable. I've sort of made some claims that sound maybe not so clearly, obviously achievable. Really, scalability without complexity? I mean, when I say that, I mean naturally. No proxies, no multiple instances and aggregation of data out of one instance. Discovery without sending packets? Really? At this point at Facebook, I asked the question, how many people in the audience think I'm full of shit? Right? So how many people in the audience think this doesn't sound reasonable? Good. I like that because that means that you're listening. If no one raises their hands, I worry that you're all asleep or perhaps have been taken over by pod people.
It means with the right target audience.
Pardon?
It means with the right target audience.
I think that most people who understand the technology involved here understand that this is not what everything does, right? Right? This is not what everybody is already doing. It also means I'm looking at an potentially interesting problem. So our two philosophical underpinnings here, the next dimension, the last dimension I can move my arm on because one time I tried to move to the fourth dimension and I disappeared, so I can't do that anymore. So monitoring and discovery are fully distributed. The central server just waits to be told that something bad has gone wrong. And we do that through a no news is good news philosophy, which is reliable. That's the key. No news is good news is good. Reliable is good. Having them together, that's the rub, right? That's the piece that's a little bit different. And it's not complicated, actually, but it's different. And so as a result, the central system only has to deal with the edge conditions, changes from wasn't working to is working or is working to isn't working. And the rest of the time, it sits around waiting for something to break. So that's kind of the philosophical underpinnings that create this. So the scalability is so simple that I can explain it so that your grandmother would understand, even if your grandmother isn't a computer scientist. So I'll explain it this way. On my church, on Wednesday nights, we get together for a meal. And we stand around and we hold hands and bow our heads and the pastor prays and we have our eyes closed. And while we have our eyes closed and we're holding hands in a circle like this, who notices if Aunt Sally passes out? The two people holding her hands. Now, and by the way, they don't squeeze hands to go around the ring to see if there's a doctor in the ring. That's not how that's done. They shout it out or they pick up the phone and they call 911, which is multicast or unicast, right? So they do that. Now the question is, how many hands did you have to participate in this arrangement? 2. Now, if I added 1,000 people to this ring, how many hands would you have to have? Did your work go up? No, not at all. Not any. So we have our computers hold hands. We don't have them pray, but they do hold hands. But holding hands means they have partners that they send heartbeats to and expect heartbeats from. But this is simple, right? And it's obviously scalable at this level, right? Nothing is ever as simple as beyond this, it's a simple matter of programming, as they say. So if you want to look at this from the computer science perspective, you draw something here. Now, I don't like, this is not a ring because when I say ring, computer scientists hear the word, which I don't say, token. There is no token in this ring. You have neighbors, and there is no token because just like the human case, you wouldn't squeeze hands to go around the ring to say, is there a doctor in the audience, right? You would instead call 911 or shout out, somebody get Dr. Jack, right? So each server monitors 2 or in some cases 4, which I'll get to in a minute, servers. And each server monitors its own services, but because I'm monitoring its liveness, its general health through its neighbors, I have a way of having a highly reliable way of knowing whether the server has gone away without asking it. I'll be told that it goes away. So in this case, for example, server A heartbeats F and B, F heartbeats A and E, and I think this is obvious, right? Is this obvious to people at this point? Yeah. And ring repair is extremely. If you have a million nodes, and you're looking at hardware failure rates alone, you're looking at 10,000 packets a day to do that work, which is pretty tolerable. Now, of course, there's a lot more things than that, but that's just to give you an idea of the back of the envelope style scaling, right? So that's the first ring I drew you is exactly how the code works today. This is how we want it to work, which is way cooler computer science looking diagram, right? There's no question this is way cooler looking. So now instead, we use I apologize to the camera people, we use the rings, the vertical rings here are per switch. So let's start with just that ring. Interesting thing about that ring, it is your cheapest bandwidth. It is the bandwidth which is most reliable. If you are losing packets going port to port on your switch, you have a problem, and it is not my software, right? And so, but of course, if the switch fails, you're not going to know, right? So, oh, that's bad. Oh, I know what I could do. We could add a ring like this green ring here, where I nominate one machine per switch on a subnet to create a second ring. Now, something very interesting happens when I do that. I have another question to ask the audience, and this is not rhetorical, right? So if this guy fails, if this box fails, how many reports will I get? It has 4 hands, right? This guy has 4 hands instead of 2. How many reports will I get? 4. Right. If this switch fails, how many reports will I get? 2. Oh, what a neat property. I can now detect that the switch has failed and distinguish it, in most cases, from the server failing without even knowing anything about the switch. Now, of course, there are lots of edge cases, and edge cases happen all the time if you have billions of servers and billions of switches, but the majority of them still look a lot like this. Now, of course, if you have so what we did in addition at the top, we created an inter-subnet ring where I nominate one machine for each subnet. And so what I really have done is created rings which match the failure domains of the network. They're at least correlated to failure domains in the network. And you can imagine, if you really had lots of different sites, you could imagine one ring at the top where you had one server nominated per site. Now, if you do that, then how much traffic is going between sites to monitor the whole darn site? The answer is not very much, right? Not very much. 2 packets a second, or a packet every 30 seconds, whatever it is that you set it to. But it's a very small amount of data to let you know reliably that you haven't lost communication with that site and that things on that site are continuing to function more or less correctly. So this is an interesting architecture where we'd like to go. And as I said, 96% of the traffic then stays within your switch. It's about 95, 96%, depending on what numbers you believe and how big your switches are. I understand Google has some really big switches, so it'd be even a smaller, higher percentage. But the point is, almost all your traffic stays within a switch. So it has a sort of elegant beauty to it in terms of matching the network and matching up to having some nice properties of diagnosing problems according to failure domains, and also to minimizing the traffic on the network. So the next architectural component, the next component here in the next dimension, the one I don't want to wave my hands or I'll disappear, is the 4th dimension, or to go to architectural components. That is to say, what architecture supports this, right? So I've described how it works in sort of wave your hands terms, which I like waving my hands. So the next dimension, though, is to talk about our 3 architectural components we really have here. I have something, because this is the Assimilation Project, of course, the agents we put on all the machines have to be called nanoprobes. And of course, that means we want to inject your machine with nanoprobes so they can be assimilated and join the collective. Therefore, the top-level system has to be called the Collective Management Authority. Now, I didn't call it a system because it may, in fact, as things evolve, become a cluster rather than a single system. But for a long time, it can be a single system. So the 3 components are the CMA, the Collective Management Authority, the nanoprobes, which are agents on all the machines you have permission to put them on anyway, and we have data storage using the Neo4j graph database. It's a reasonable database and an excellent, I think they do a good job of managing it as an open source project. So the CMA itself, going on to talk about the CMA itself, it is written in Python, because I like Python. And really it does three things. It manages the nanoprobes, which is most of its job. It updates the database, which is part, you could argue, is part of the nanoprobe management business. And it issues alerts. That's all it does. That if you think about it, that makes sense. Now there's a GUI that hasn't been written, and when that exists, it will hook into here as well. But it probably actually won't be part of the CMA anyway. So these are, this is all it does, right? And I'll talk a little more about the nanoprobe management. For example, it is the CMA, which, by the way, I didn't mention this. I'm happy to take questions during the talk. I'm sorry, I didn't mention that. So don't hesitate. From now on, don't hesitate to ask questions, because I'm happy to answer them. And it's a lot easier for you to not hold the question, but to get, yes?
This is implemented now?
Just the one ring, but everything else is implemented, and I'll do a little demo in a bit, okay? And you can see some of what's, yes?
So I can understand how that topology of the previous slide would work if most of the time all servers are up. But if you've got a large number of servers, then at any one point in time, there will be a subset of those servers that are down for the next week, 2 weeks,
yes,
maintenance or whatever. Now, if one of the, for example, the inter-switch designated nodes is down...
those are assigned by the CMA. Those are assigned by the CMA, and we assign a new one if it goes down.
So you'll need a protocol. Now, the protocol to reassign, is that directly from the CMA?
Yes, we made that choice for security reasons more than anything else, and simplicity.
Right. Okay, so there's the nano
that works.
Listen for commands from the CMA.
Yeah, I'm about to talk a little more about the nanoprobes are policy free, and they don't know anything at all about the topology. Nothing about the topology.
Right.
They're just told they know about sending heartbeats, they know about expecting heartbeats. That's it.
Right. So if you end up with a one-way communication to a node, can't you end up with this breaking down? Because with some types of routing errors, you can end up that A can talk to B, but B can't talk to A.
Yes.
So you could end up with a command saying take over that role, or lose that role.
But I get ACKs back, and if I don't get the ACK, I eventually mark the machine as dead.
Right. So they're datagrams, or is it a stream protocol?
They're datagram. I'm not sure I want to give all that detail right now.
Okay.
It's a good discussion, but we only have so much time.
Sure.
It's an excellent discussion. And the short answer is I use UDP with a reliable transport protocol over it. I mean, that's the short answer, right?
Okay.
Because you hardly ever expect to hear anything from these guys. They'll go months or years with no packets from them. It makes no sense to keep up a TCP connection for years.
Yeah, that makes sense.
So update the rings. So that's update rings, join and leave, right? That's the CMA causes that to happen in the nanoprobes. They're in charge. For the most part, you have to expect, just like you said, a certain percentage of your systems have been taken over by bad guys. And you want to survive in that case as well. You don't want to do the worst thing you can do, so you give them as little trust as you can get to get the scalability and no more, right? That's sort of my philosophy. People say, oh, well, I have protocols that deal with this or deal with that. So I'd rather go simple and say, give them as little trust as possible. The nanoprobe functions are in C. They do two things. They announce themselves to the CMA. They say, hello, here I am. And then they wait to be told what to do. If they announce themselves and are never told to do anything, they do nothing. They do nothing. So they receive configuration information, for example, that tells it where the CMA is and various ports and protocols to use for different things, right? And they're told to send and receive heartbeats, send and expect heartbeats, I should say. And they're told to perform discovery actions, and they're told to perform monitoring actions. And at the moment, the implementation has no persistent state across reboots. And in fact, by the way, they have no configuration with one possible exception. And that exception is if in your network they can't locate the CMA automatically, which can happen in some cases, then you'll have to tell them how to locate the CMA. But for many people, I went to IANA and got a multicast address that's dedicated to the project. So they wake up and they send one packet to the multicast address saying, hello, CMA, where are you? And then the CMA responds back with the configuration information, and then everything goes on unicast after that. Yes?
How are you handling security if you don't have any configuration?
When I put the protocol in for security, I will have to distribute certificates. Yeah. Would you like to come along and implement that for me?
No.
Well, darn. But that's why I'm here, right, is to ask those questions, right? I don't know why you're here, but that's why I'm here. So we do service monitoring based on the methodology used by the Linux HA, Heartbeat, Pacemaker, whatever you want to call it, system. We have re-implemented something called the local resource manager, which basically says, I'm going to monitor my services on my machine myself, right? So if, for example, I have a web server, it will do a wget every so often. If I have a database server, it will do a query every so often, and so on, right? But it will do it locally, not over the network. But keep in mind, if this daemon goes away that's doing this, well, everyone will know because it will stop sending heartbeats. We implement the Open Cluster Framework and some others, and we'll do more in the future than we have so far. As I said, each system monitors its own services. In addition to being able to monitor services, this protocol is also, these APIs are also allowed, also implement the ability to start and stop services, which is a nice thing, right? Monitoring is good, fixing things is better, but I'm not prepared to do that. You know, it's crawl, walk, run, right? We're still at the crawl stage, so we're not quite. So the pros and cons of our monitoring. Is it simple, relatively simple and scalable? We have an extremely uniform work distribution. It's fair as fair can be. And it has no single point of failure. Even if one machine fails, the other two machines are still being monitored by their other peers, right?
Isn't a CMA a single point of failure?
Yeah, you put it in an HA cluster or something. There are a variety of techniques to solve that problem. And I did HA for 15 years. I know those techniques, but I don't plan on re-implementing. I would use somebody else's package to do it, right? It works fine. CMA would be if you couldn't make it HA, but it's easy to make it HA. And I've designed some things so that some of the little edge cases are things that are done right, because you can do them wrong and lose data sometimes. So we have the option of distinguishing switch failure versus host failure in the future. It's very easy, extremely light on the LAN and the WAN. For the WAN case, where you have multiple sites, man, it's just nothing, right? It's nothing. And we have implemented a sort of multi-tenant approach. It's not all fully deployed, but it will be. The disadvantage is active agents. If you hate active agents, you're going to hate this. Be done with it, right? You're going to hate it. Okay, you hate it. It also has a potential slowness at start power on. So, for example, if what you're doing is starting 30,000 virtual machines and letting them run for 5 minutes and starting 30,000 more, we're going to spend a lot of time reorganizing these rings, right? We're going to do a lot of work doing that and rediscovering and everything else. So that's the disadvantage of this, right? That's the disadvantage. So why did we use a graph database? That's a question people ask. And it's a good question. The first answer is, when I ask you, if I were to pick somebody here and I say, you describe something about one of your systems at work, right? You'd come to the board and you'd start drawing circles and squares and arrows. That's a graph. So the way you think about things is most commonly expressed as a graph. I don't know how people think of things, but that model is common to use to communicate between people. So the thing about my experience with software, when the software thinks about things the way I think about things, I have a lot less trouble with it. So having the software model matched by mental model is a good thing. Dependency information is fundamentally a graph. When you talk about, one of the questions you want to ask commonly is, I'm going to take this server down for maintenance, what all might be affected? Or maybe you have a dozen servers that have gone down at once. You think there must be something in common. So you say, tell me all the things which these 12 servers depend upon, which isn't also down. And that is to say, which things are broken but depend on nothing else that's broken. Oh, those are probably your root causes. At least they're the place to start looking for root causes. So root cause queries then become graph traversals, and those are notoriously slow in relational databases. They are basically join and join and join and join and join until you stop getting a bigger answer. And that's slow, right? And one of the nice things about a schemaless design, and this is not a graph database per se, but most of the NoSQLs, is that as things evolve in your data center, how many people here have all the same versions of hardware on all their machines? How many people in the room have all the same levels of firmware on their servers? How many people have, one person? How many people have all the same levels of firmware on your switches? Two people, three people. So the point is that it's not that common. And with the diversity, what that means is as you add new things, if I want to model them, I have to then stop the graph data, stop a normal database, restructure it to add the fields to describe this stuff, and start it back up. Well, with a NoSQL database, you can just add fields as you please, right? You can add the data and away you go. Visualization is sort of natural. One of the things we hope to be able to do is I can create graphs. I forgot to pass them out, actually. Here, take this and look at it and pass it around. There's another one on that in front of you there. So I can create graphs that terrify people. That's easy, right? Creating graphs that terrifies people is easy. This is 4 systems at my house. But creating graphs that provide aha and insight is hard. But if you have the data, you have the opportunity to do that. And that's one of the things I think an open source project with the iterative process of creating things, having people bitch about them and correct them, and going through that process is very good at doing. And hopefully we can advance from terrifying graphs to insightful graphs over time. So to go to the next dimension, I want to talk about, so I've kind of given you a mouthful here, a brain full of stuff. How many people here still have questions? What questions do people have at this point? I want to stop and take a second for that. Yes, go ahead.
You said at the moment the first ring is currently implemented.
Yes.
It would be good if you could explain at least as far as that has been implemented, such that we could go away and do it ourselves.
So explain which?
What's implemented so far?
So I will cover that in a little more detail. I have a slide of that on the end. And I'll do a little demo. So, question?
Just a question. You said about 30% of everything's square.
There's a Verizon study that says that.
Yeah. So if that's the case, and it's an active agent.
So we listen to art broadcasts.
Okay.
As I said, you just have to listen. The data's there, right? Just listen to it, right? Just listen. I'm sorry, yes.
So everything you're describing so far seems to be based on traditional data center architectures.
Yes.
How well does this work in an environment where you may not necessarily have control over that traditional architecture, such as a cloud topology, where your switches and your routers, your servers, etc., may not necessarily be discrete devices?
Well, first of all, you probably have virtual machines instead. But I would say what happens is some of the things I use to discover some of the data don't provide that data, and you don't have that information. I don't think it breaks. I think it's just that it doesn't provide you the full richness of all this stuff, right? That's all. Depends on what all things you can get and what you can get your vendor to help you with, right?
So in terms of the ring topology, it's not
Ring topology. First of all, I don't even guarantee you have LLDP or CDP deployed, and if you don't, then the ring topology will change a little bit. Basically, everyone then joins the subnet because you always know what subnet you're on, and so you don't get all the benefits. But if you can, you get more benefits. If you can't, you get fewer. I think it scales up and down in that respect nicely, or at least it should, in theory, when one writes code. Right? Yes. Question in the very back. I'm sorry? So IPv6, if you have IPv6 only, then we can't, there's some things here that are, like, for example, discovering, so with if you have an IPv6 only, then I'm not hearing ARPs, right? So I can't discover systems like that. The good news is probably neither can your attackers because you have a 64-bit address space that they have to search to find your machine. So, I don't have an answer to that question yet. I'm not, but by the way, the code only deals with IPv6 addresses internally, period. Even if it's an IPv4 address, we map it to an IPv6 address to deal with it. So the code is fully IPv6 compliant. It's just that I don't know how to do some things in IPv6, and not sure I know anyone who does in some cases. So I'm going to talk about how the scripts perform discovery, and I'll give you 3 sample JSON outputs. Basically, they're scripts written in whatever scripting language you want, and they spit out JSON to describe whatever it is they're discovering. And I don't discover the whole system, I discover aspects or dimensions of the system, right, separately. And I'll give you a sample OS information, sample service discovery, and sample server discovery, listening port discovery. Oh, it says I'm going to do a demo here. I've never done the demo before, ever. I mean, in public. Let's see if I can switch over here. So what I'm going to do here, I have to switch to this window. If you don't have bifocals, it's hard to appreciate how annoying they are. I'm going to start up the CMA here, and I'm going to tell it to erase the database. There is no configuration in the database, and there will be none given to any of their tools, right? And I'm doing this without a wire. You know, I'm doing it up in with no net, right? So this will start the CMA. Oh, it wants to know my password. So it's started up, and now it's going to wait for a nanoprobe to connect to it. So let's start a nanoprobe, and I'm going to tell it to. I told it tput, apparently. Anyway, I didn't tell it anything. So now it starts up, and it has local address, and it's assertion RC equals. Oh, I have to have a local network. I forgot. Dang it! I have to have a network, or it won't work. And I have my Wi-Fi isn't working. So why don't I skip this, and we'll try to see if I can do it at the end because I forgot to put my Wi-Fi card in. Sorry. We'll skip this. It basically what it amounts to is it can't. Oh, a wired network. Oh, how much better is that? Okay, let's see what happens here if I have a wired network. Because it wants to send to the multicast address, the one I got from Ayana. Right, so let's see what happens here. Oh, it's starting. How good. If you notice here, it lists local address is : for the IPv6 people. So let's go back here and see what's going on the... I was listening and it's not hearing anything from this guy. That's bad, isn't it? Oh, maybe it was listening on any...
Has it actually got a...
Yeah, well, it didn't have an IP address at the time. I think I have an IP address, so it would complain. 1, 2, 3. I'll try starting this again. Connected to the CMA, happiness. Okay, now what's happened here is that over here on the CMA side, it has said, so that's saying more stuff. Oh, invalid network address type that's interesting. I've never seen that before. Isn't that wonderful? So anyway, if you see at the top here, it says what's off the screen is the fact that it discovered that it's running Neo4j, it's just running the Munin node, and it's running RPC statd and some other things, and it knows how to monitor some of those and not how to monitor others. And now as it goes on, yeah, there's something wrong here. I haven't done this. What if the network address type? Well, that's interesting. I don't know what that means.
It looks like a MAC address that's blown up.
Well, anyway, it looked like it worked earlier today. I can tell you. So anyway, it mostly works. So.
That wire may not actually be working.
Well, anyway, whatever it is, we're going to go on and do other things. So sorry about that. That's the problem. The insanity of trying to do a demo for the first time. But I guess there always has to be a first time. So, no. I didn't really mean to start my email client. No, go away. So, okay, back here. Now we'll go back to F5. And apparently, oh, that's just the wrong one. Alt-tab. Is that the right one? No? That apparently does. Well, this is really good, you guys. You know, I'm just so impressive, aren't I? Alt tab. Yeah, thanks. Okay, let's just get rid of this.
Trying to get it full screen, huh?
Yeah, I'm trying to get it full screen. I pressed F5 and it didn't do anything.
Toolbar to the right of your...
Yeah, but I already pressed F5, which should have brought me. No, it's F5 on this guy. So let's go slideshow. apparently start from current slide is already done, so let's start from first slide. I'll just skip down. I don't know why it doesn't want to start from the current slide, but okay, well, so I told you how the discovery works kind of, and I skipped it. So anyway, this is what the discovery snippet looks like from an OS discovery. What operating system am I running, what version, and this is the output from a script called OS, I think. You know, the node name, the operating system. This is uname type stuff added with some LSB type stuff that tells me things like the code name and the actual name of the operating system I'm running, which is always good because I always forget these Ubuntu names. Raring is which what? You know, I have trouble with this. So it discovers all these things and they all go into the database. So if you can write a script that spits out JSON like this, then you can write a discovery agent. It's not hard. So here's an example of the output from SSH, from discovering a service running on the machine through the, I forget what it's called. Anyway, I have a script that does this. I've renamed it 3 times. So this tells you that we have an SSHD listening on port, actually the output's a little different nowadays, but listening on any port 22. And the interesting thing is, in addition to knowing what port I'm listening on, I know exactly what binary is on there, what executable, what arguments it was invoked with, user ID, group ID, current directory, and so on. So I learn a lot more about this than just, oh, I have port so-and-so open. I know what's on it. And that's important because that's part of what I use to decide that this is a particular service that I know about because I see it, I look at the arguments, and I say I know exactly that I'm running SSHD here and not something else on port 22. So on the client side, you can do something similar. Except now, instead of being able to have an any address, you have to have a concrete address. This is an SSH calling out. So it's SSH, but the user ID is Alinar instead of root, and it's SSH to a particular machine called Servidor. And my home directory was, oh, look at that. It's the home directory is my source code. And it has something similar, but I'm going to 10.10.10.5 port 22, which means I'm calling back to the machine that I was on.
Excuse me, does that count as an event every time a client starts?
So in terms of services, I have some work to do here in terms of keeping the noise down. The answer is yes at the moment, but I don't like that answer.
Not necessarily a bad answer as long as you tune it later.
Yeah, right. Yes is the short term. Yes is the answer today. So the interesting thing, though, is now so this is the data I collect. Well, what does it look like when I put it in the graph? And there's some interesting things that happen when you put these together in the graph. The first thing I'll do is put those 2 pieces of discovery information I did. This is the SSHD discovery, which says that it is running on Servidor. It is listening on 10.10.10.522 and 10.10.222, right, through the TCP service relationship. And that those in turn, 10.10.10.5 and the other one are both part of their respective IP addresses, which are also owned by this NIC, and this NIC is owned by the server. So this is the kind of information that comes in the schema. But I also have at the top there, where I couldn't possibly reach it for a short guy like me, the SSH calling out. Now you see that it has a TCP client relationship to that 10.10.10.522, which has a TCP service relationship to SSHD. And oh, look at that. I have an SSH which depends upon the SSHD. Right? The 2 pieces of data, when you consolidate them all together in one place, interesting things become learnable, discoverable about the whole system and how it behaves together. And as was mentioned, this is not all soup yet in terms of particularly the client side. The server side's easy. The client side, not so easy yet. I'd like to do some interesting things on the client side. I have had some suggestions, but we really need to move on. So discovery for LLDP looks kind of similar, but now instead I'm talking to switch ports. So I have a wired to relationship between NIC ETH0 and this switch port G3, which is labeled by the switch kitchen north wall white jack. Everything on here was discovered. Nothing was input to my program. I did tell the switch where that port went, but then you can see how all of these things come together, and I can now see where this switch port is plugged into which switch through LLDP or CDP. The next dimension is the current status, which was asked about. We have great unit tests. The nanoprobe works quite well. Several discovery methods have been written and work fine. I've completed restructuring the CMA. Actually, at this point, that's probably... Yeah, okay. Yeah, so anyway, we have user interface development underway. Currently, a license under the GPL option of changing license or offering another license. We need lots of different kinds of talents. We particularly need early adopters. The point here is to have you come engage with the project and help us out with it. So thanks very much for your time.